morning, everyone. Welcome to the ASME JCISE Journal Computing Information Science Engineering JCISE Spotlight Talk for this month. And today, we're pleased to have two speakers and to give a presentation on the recent paper published last month, August issue. The speakers include the Professor Sundar Kumara. Professor Kumara is Alan Pierce Professor of Industrial Engineering at Penn State. Professor Kumara is a pioneer in smart manufacturing. If you are in the field for long, you will notice he was the one of the first pioneer researcher apply AI in smart manufacturing over 30 years ago. I learned those when I was even a grad student. Professor Kumar received numerous awards in the past 35 years career academic. Numerous awards, best paper awards in both communities, ASCME and Institute of Industrial and System Engineering, IISE. The most recent distinguished awards was last year, and Professor Kumar received both Research and Excellence in ASME CIE division, as well as IISE Distinguished Research Award in the same year. So today we also have the first author of the paper, Dr. Michael Hoffman. Dr. Hoffman recently received his PhD from Penn State under Professor Kumar last year. He was a research fellow, graduate research fellow of smart manufacturing in NIST, National Institute of Standards and Technology. Dr. Hoffman right now is a data scientist on the machine learning data analytics and working for US federal government. And today, they're going to give the talk of their paper published. The title is Online Maintenance, Prioritization via Monte Carlo Tree Search and Case-Based Reasoning. Professor Kumara.
Thank you very much, Dr. Wang, and for your kind introduction, and thanks for those who are attending. I'm going to start the presentation and pass it on to Michael, who is the first author of this paper. And it's been a privilege to work with Michael, and it's also our privilege that JCISE picked our paper to spotlight, and thank you very much. So when you look at maintenance, which is one of the classical problems, and then it's also a well-researched problem. So one of the important things here in terms of the solution prioritization is which machine or which activity we need to maintain. So in order to do that, we kind of looked into two different aspects. One is the case-based reasoning and also Monte Carlo tree search. So when you think in terms of the solution space of this maintenance prioritization, to navigate the solution space in a finite amount of time, in real time becomes extremely critical. Therefore, this particular work addresses that little but significant aspect of maintenance. So with this introduction, I'm trying to pass the baton on to Michael, who is going to talk about some of the details. Thank you, Michael.
Yeah, thank you very much for the intro, and thank you for the opportunity to give this talk today. So as was mentioned, this is a paper that I put together as part of my dissertation research at Penn State under the advisorship of Dr. Kumara, as well as Dr. Song. And Dr. Michael Brundage also served as a co-author for this work. So We've titled this work Online Maintenance Prioritization via Monte Carlo Tree Search and Case-Based Reasoning. As Dr. Kumara mentioned, the focus of this is really on solving the problem of prioritizing maintenance activities in a manufacturing system. So to give a quick overview of what I'll cover today, I'll give a quick background and some motivation regarding the practice of industrial maintenance. I'll describe the model that we use for our manufacturing system that we study, as well as the maintenance model within that system. I'll then describe how we use Monte Carlo tree search to prioritize maintenance activities in the system. And then lastly, I'll describe how we use case-based reasoning to improve that maintenance prioritization procedure. So a quick background on industrial maintenance. Maintenance can refer to a lot of different activities and practices depending on the domain and the system of interest. Generally, in the case of manufacturing, it refers to ensuring that our assets remain in their expected working condition. So that includes ensuring things like sufficient quality, production rate, ensuring safety measures are met. And depending on the maintenance strategy that's in place, it can include a fairly wide variety of different activities. So things like repairs and replacements of parts, also things like inspections and condition monitoring. All of these fall under the umbrella of the maintenance function within a system. But regardless of the particular maintenance strategy that's in place, we generally make the same assumptions when examining maintenance. So the first assumption is that the machines that we're maintaining degrade over time and eventually incur some occurrence of failure. These failed machines can only be restored by what we characterize as a corrective maintenance job. Otherwise, a machine that has not yet reached that failed state can be restored by a preventive job. So every maintenance activity we classify as being either corrective or preventive. And in general, we assume that corrective maintenance is more costly than preventive maintenance. And that's largely due to the extent of the damage that occurs with complete failure and the extensiveness of the maintenance activity that's needed to correct that complete failure. So in particular, we study multi-component systems, which introduce some additional challenges when looking to optimize maintenance. The first being that we're faced with an exponentially increasing solution space. And that's due to the fact that for every additional machine that we include in our system, we have an additional set of decision variables that we need to determine in order to effectively conduct maintenance on that machine. So with each additional machine that we study, our solution space grows exponentially. Another aspect of multi-component systems is the dependence among these multiple machines. There has been some previous work to characterize these various forms of dependence, but I'll just point out here that we focus on mainly structural dependence in the form of performance dependence, which I'll describe on the next slide, as well as resource dependence in terms of some maximum maintenance capacity. Now, performance dependence refers to the impact that the configuration of machines has on the performance of other machines in the systems. So when I talk about the configuration of machines, I'm referring to, for example, a serial arrangement of machines or machines that are arranged in parallel or some combination of these aspects. Now, most prior work on maintenance optimization generally assumes some strict system configuration. That is, they assume that machines are arranged either in series or parallel. And that makes it very difficult to generalize these methods of optimization to systems of arbitrary configuration. So that's one of the goals of this work, is to allow for a maintenance optimization procedure that could be applied to machines in any configuration. We also consider a capacity dependence, which limits the number of maintenance jobs that can be conducted simultaneously. You can think of this as a system with a limited number of maintenance workers, which sets some limit on the number of machines that can be repaired at the same time. And when we include this form of dependence in our system, it introduces the additional problem of having to prioritize maintenance jobs when the number of machines that require maintenance exceeds our capacity to do maintenance, and we must choose which among those requesting maintenance should be serviced first. Now, this is just a summary of some of the previous work that looks at both forms of dependence and multi-component system dependence, specifically for condition-based maintenance, which is what we examine here. So some work has considered either performance dependence or capacity dependence in isolation, but at the time that this paper was published, we're not aware of any work that has considered both forms of dependence simultaneously. So now I'll describe the model of our system that we study. An important component of that is our degradation model for machines. So we use a discrete time Markov process to model the degradation of each machine in our system. So each machine begins in a state of perfect health, and according to some degradation transition matrix, which is on the right here, the machine will gradually transition into states of increased degradation. So this degradation increases until either it reaches a maintenance threshold, which is indicated in the figure here. So this would be a preventive job that we're conducting before the machine fails to restore that machine to perfect health. Alternatively, if the machine reaches complete failure, then we need to conduct a corrective maintenance procedure, which again restores that machine to perfect health. So we apply this degradation model to all of the machines in our system. To model the maintenance priority problem, we use a maintenance queue to maintain the set of all machines that request maintenance. So in this figure here, we're showing, just as an example, a FIFO queue, so first in, first out. Machines are repaired in the order in which they arrive to the queue. So this introduces our maintenance prioritization problem, where we have to decide which machines in our current maintenance queue should be repaired first. So we can apply common queuing methods, which I'll show in some of our experiments. So using FIFO, like I mentioned, we can also choose to prioritize corrective jobs or preventive jobs, or vice versa, things like that. So to model the system behavior, we use a Markov decision process model, which essentially is defined by some state space, which defines the state of our manufacturing system. Our action space, which is the set of maintenance actions that we're able to take in the current system state. We also have some transition function that determines our transition between states given an action that we choose in the current state. We also have a reward function, which in the case of our manufacturing system, we define as the total throughput of the system. So that's the reward that we're trying to maximize. And we also apply a discount factor, which is common in these MDP formulations. So we model this reward function using this Q function formulation, which essentially returns some reward value given a state action pair. So that gives us the long-term discounted reward over some time horizon. So the behavior within this Markov decision process is defined by some policy, which maps every state to some action. So in our case, every state of the system would be mapped to some maintenance action that we are executing in that state. And that includes the action of choosing to do nothing. So it could be the case that we're in a state where we choose to take no maintenance action and simply let the system transition to the next state before we make another decision. So in the case of our manufacturing system, our state space is a function of the degradation state of each machine, according to the degradation model that I showed previously. Also the elapsed processing time at each machine, since every machine is continuously processing parts. The current elapsed repair time for maintenance jobs that are currently in process in the current system state. And also the distribution of buffer levels within the system. So the buffers retain parts in between each processing station. So the levels of those buffers will dictate the system state as well. As I mentioned, the action space consists of maintenance actions, which includes both preventive maintenance requests as well as the set of failed machines that require corrective maintenance action. So given this system model and the problem formulation, I'll now discuss how we use Monte Carlo tree search to conduct this maintenance prioritization. So the goal here is to find some optimal policy under this Markov decision process formulation that maximizes our expected long-term discounted reward, which is defined by our Q function. And this pi of S is our mapping between system states and maintenance action. So we're looking to select the maintenance action in every state that will maximize our expected reward from that state. Now this type of problem formulation is commonly used in reinforcement learning, and that's where we sort of take inspiration for our particular solution method. So in a typical reinforcement learning formulation, we have some agent which makes decisions in the system, and as that agent makes decisions and gathers observations that result from that particular decision, it will gain more experience and improve its policy over time. So this is an iterative procedure. As the agent makes more decisions and gathers more observations, it eventually converges on an optimal policy. However, in our case, taking experimental actions is relatively expensive in a manufacturing system. We typically want to avoid taking these experimental actions in order to gain more observations to improve our policy. Because if we make a poor maintenance decision or neglect to repair a critical machine, that can severely impact our overall system throughput, which has very serious real world implications. So to amend this reinforcement learning formulation, we introduce a simulation model. Now this model allows us to conduct some planning activities. And we define planning as evaluating alternative action sequences by using this simulation model to gather experience. So if we can assume that our simulation model is a accurate representation of our real world system, then we can conduct our experimental maintenance actions using this model without impacting the productivity of our real world system. Now our environment model, going back to our MVP formulation, which includes the transition and reward functions, in many real world systems, these are unknown, and this is just due to the large state space that we're dealing with, as well as the randomness among the transition among states. So we don't know for certain what our transition and reward function look like. There has been work in the field of reinforcement learning to estimate these functions. However, given that our system has such a large state space, we're dealing with something on the order of millions of states. It's not feasible to estimate these functions and the transition probabilities among every pair of states. So instead, we use our simulation model to act as a generative model. So this simulator, when given a state and an action executed in that state, it returns some sampled future state. So now we can strategically choose which states and actions to sample using our simulator in order to best estimate the optimal action given the current state. So this is what we refer to as the prioritization problem. And it's really a combination of both reinforcement learning and that planning procedure where we sort of interleave the planning phase and the action execution phase. So for every maintenance action, we conduct some search of our state space in order to find the best action in the current state. We execute that action and our system then transitions to some future state and we conduct the planning again. Now, in order to sample this simulator and seek the best action, we use Monte Carlo tree search, which progressively constructs a search tree of our state space. And it does that by sampling alternative sequences of actions in states, given the current state of the system. So part of the benefit of this approach is that it balances exploration of less visited actions with the exploitations of actions that we deem to be promising. It also avoids expending simulation effort in under-promising regions. And given that we're looking to make maintenance decisions as quickly as possible, we can use our computational budget much more efficiently using MCTS. Monte Carlo tree search is also ideal for seeking the best action in large state space MDPs, which is what we're faced with here. And that's because it allows us to avoid having to enumerate the entire state space. So we can only model the subsection of the state space that is most relevant to our current state, and only model what is actually going to help us make the best action in the current state of the system. So this is just an overview of the Monte Carlo tree search procedure. So at each iteration of the search algorithm, we select a node of our current search tree according to some tree policy, which I'll describe in the next slide. We expand that node by selecting an action from that selected state. We simulate out that expanded node to obtain some reward, which we then backpropagate through our search tree. So at the end of each iteration, we've added one node to our search tree. So we continue this procedure until we've expended some simulation budget, whether that's some maximum walk lot time or some maximum number of iterations. So for the tree policy, which dictates how we select nodes within the search tree, we use the upper confidence bound for trees. And this essentially is that exploration trade-off function. So it considers both the reward estimate for every state, every candidate node, as well as the number of visits to each node in the current tree. So this is an overview of sort of where MCTS fits into the overall workflow. On this left gray box is the process of the condition-based maintenance policy optimization, which is covered by much of our previous work, which I would encourage you to go read. But this work really focuses on this far right box of the online policy improvement. So given that we're faced with some maintenance conflict, we use MCTS to determine the best action. We return that best action to our current real world system state and execute that maintenance action. And then we continue to operate our system until we encounter another maintenance conflict. So for our experiments, this is an overview of the system that we examine. So we have on the top right here a 9-machine system. So we have some condition-based maintenance policy, which determines the maintenance threshold at which we request preventive maintenance for these machines. In the case of the experiments that we conduct in this paper, we collapse all of these parallel stations down into a single station. So we apply the same maintenance threshold to all the machines in the within a station, since we assume that these machines are identical. And that just helps us to reduce the size of the state space and help us to more quickly find a good maintenance policy for the system. Now, these are the experiment settings. We vary things like the degradation rate of the machines, our capacity for maintenance. So again, the maximum number of maintenance jobs that we can conduct simultaneously. We also vary the distribution of corrective times to repair, and then also the number of machines at one particular station. So we're looking at really 2 systems here, one with 9 machines and one with 15 machines. And then at the bottom here, this is just the degradation matrix that we apply for each of the machines in the system. Now, some of the alternative scheduling rules that we compare our method to are classic queuing rules. So first in, first out. We also look at shortest processing time first. So we prioritize machines that we expect to be able to repair more quickly. And then conversely, longest processing time first. So we prioritize machines that we expect to take longer to repair. We also use this concept of Birnbaum importance. So this metric attempts to quantify the structural importance of components in the system. So it essentially will prioritize machines that are more likely to impact the overall productivity of the system. So the goal with this heuristic is to try to maximize our system level throughput, which is the overall objective of our optimization problem. Now this is the result of one particular system configuration that we studied. So on the left here, we're showing the policy optimization, which in our prior work we have done using a genetic algorithm. So after 250 generations of that genetic algorithm, we've obtained what we consider to be some optimal policy, which takes the form in this bottom left here. This X of S is the maintenance thresholds that we apply to each respective machine in the system. On the right, this is showing the system level throughput of this static policy using that Birnbaum importance metric compared to our method of online improvement. So on the right here, this blue line is showing the result of resolving these maintenance conflicts using Birnbaum importance, whereas the green is showing the throughput that's obtained using Monte Carlo tree search to resolve these conflicts. So we're able to significantly improve the overall throughput of the system using our method. This is just a summary of the results, which we describe in more detail in the paper, but given the problem space that we've examined, our method improves the overall throughput of the system in the large majority of cases. And there's only a few instances where we're not able to do better in terms of overall system throughput. So now to improve upon this online maintenance prioritization, we use case-based reasoning to improve the efficiency. So as some motivating factors for applying case-based reasoning to this problem, firstly, Monte Carlo tree search is relatively expensive computationally. It takes a decent amount of time to find a sufficiently optimal action in a current state. And that's because we're simulating thousands and thousands of alternative sequences of actions. So if we can alleviate that computational expense, that would let us make maintenance decisions much more quickly, which would have a significant amount of benefit to a real-world manufacturing system. The next point here is that small differences in system state will likely not affect the optimal action in that state. So if you recall the factors that define our system state, for example, looking at the levels of buffers in the system, if the only difference between two system states is that their buffer levels differ by just a couple of units, then that's likely not going to have a huge impact on the optimal maintenance action in that system. So we would like to somehow aggregate these states and identify that those states are sufficiently similar. The last point is that our system state distribution is dense near the steady state. So I have a figure here showing the distribution of buffer levels in one of the systems that we examine. And this is just showing the density of the time that the system spends in these states. So you can see in each case, these are just various levels of time to repair distributions, but in each case, we sort of gravitate to some steady state buffer distribution. So if we can effectively retain the solution that we derive for this steady state, then we can avoid having to resolve Monte Carlo tree search every time we revisit that state. And that's where case-based reasoning is able to help us. So the premise behind case-based reasoning is that similar problems typically share similar solutions. So similarity in our case is defined by the similarity of system state. So we can use a case base, which we denote CB here, as a set of cases that retain the description of the problem as well as the associated solution. In our case, we represent problems as system states, and the solution would be the optimal action in that given system state. Now, each case in our case space is defined by this tuple here. So we have some state vector, which represents the state of the system. We have some maintenance action, and we also have some confidence level that that particular action is optimal in the current state. So given that Monte Carlo tree search collects a sample of rewards for every candidate action, we can derive some statistical measure of confidence that each of those actions is optimal. So the way that we determine this confidence in each candidate action is we generate some regression models to predict each action's confidence when we encounter a new state. So we use this is essentially the statistical formulation of the reward function, which allows us to derive this statistical probability that each action is optimal given the current state. So this is an overview of the case-based reasoning procedure as we apply it to our problem. So when we encounter a new problem, which would be a system state in which we need to make a maintenance action, we first retrieve the set of relevant previous cases that we've encountered from our current case base. We adapt a solution given those previous states to fit our current problem state. And then lastly, we can optionally retain this newly encountered state if we determine that we think that's one that's going to help us solve more problems in the future. Now, the first step is to retrieve the existing cases that are most relevant to our target problem. So we measure similarity using some distance function. So our state space is represented by some numerical vector. So we can use this Minkowski distance metric to measure the similarity between states. Now, given that we've retrieved the set of relevant states, now we need to reuse the solution that we've applied in those states to fit our current system state. So the procedure is essentially to look at these k relevant states and predict the confidence that each candidate action is optimal. And we do that using k-nearest neighbor regression. And we're looking to determine the action that exceeds some threshold here, zeta. And if we cannot determine that any action exceeds our threshold that we set, then we can always fall back and conduct Monte Carlo tree search. So the last step in the CBR procedure is retaining states. So when we encounter a new case, CI here, we can add that to our current set of states. If our case space exceeds some maximum size, then we have some various criteria by which we can evaluate each case in the case space. And we retain only the cases that we essentially think are best or most useful to our case space. So now the experiments that we conduct, we first simulate each system and use Monte Carlo tree search to resolve maintenance conflicts. And we gather some initial experience using these pilot runs that we use to tune our KNN regressors to do that reuse procedure in CBR. We use what we call the probabilistic classification accuracy to evaluate each of these regression models. And that's just defined as the proportion of predictions which are either correctly above or below our retrieval threshold. So once we've tuned each of these regression models, we can continue simulating using our combined MCTS and CBR method. So for these experiments, we do use a simplified machine model, still using the same Markov degradation process, but we consider Bernoulli machines, which essentially have two states either working or failed. So that sort of simplifies our state space a little bit. Again, this is a diagram of the system that we study here, looking at a 9 machine line, rather arbitrarily configured. So again, we use a few what we refer to as the baseline maintainers. These are static queuing heuristics, queuing rules that we apply to resolve maintenance conflicts. And we also evaluate a number of what we call the CBR maintainers. So looking at just MCTS, which is what I've showed in the previous set of experiments. We also evaluate different retrieval thresholds here. And this KNN 100 indicates that we limit our case base to 100 cases. Now, this is a result of one of our pilot runs that we use to tune our regressor. So the takeaway here is that our overall accuracy for this particular maintainer is 80%, which indicates that 80% of the time we're able to correctly identify the optimal maintenance action in the states that we encounter. Now, the 20% of the time that we do not identify the optimal action, it is possible that maybe we identify the second best action, which could still have very good outcomes in terms of throughput. But we don't necessarily quantify the quality of the action that we choose. We're just trying to maximize the proportion of time that we choose the single best action. Now, this is the result of these experiments. On the left, I have each of those static maintainers that we evaluate. So these are using static queuing rules. On the right is our throughput in terms of number of parts per hour produced by the system for each of our CBR maintainers. So you can see here that each of our case-based reasoning maintainers performs better than the best static maintainer. So in every case, we are able to pretty substantially improve our system throughput by using this case-based reasoning procedure. Another important result from these case-based reasoning maintainers is the efficiency in which we're able to make maintenance decisions. So you can see on the left here, this is showing the proportion of actions that we're able to retrieve from our case space. And that's as opposed to actions that we have to determine using Monte Carlo tree search. So if you recall, one of the objectives of using this CBR procedure is to avoid having to solve MCTS, given that it's relatively expensive computationally. So as you would expect here, this yellow line is our lowest retrieval threshold. So that's sort of the easiest retrievals come from using the lower retrieval threshold. So we retrieve a higher proportion of actions as we lower that threshold for retrieval. The right is showing the decision time that it takes to make each maintenance decision. So across the top, you can see the purple is the Monte Carlo tree search time. So on average, it takes us about 12 seconds to make a maintenance decision using MCTS. And that doesn't ever get reduced, because even as we gather more experience, we're conducting MCTS at each decision point. So we're not improving our efficiency in terms of our ability to make a decision. However, for each of the CBR maintainers, you can see over time, as our maintainers gather more experience, we're able to make decisions more quickly. And that's because we're retrieving a higher proportion of existing solutions from our case base, which is very important if this is something that is implemented in a real world manufacturing system, since ideally you'd like to make maintenance decisions as quickly as possible. So lastly, I just have a couple points here of future work. The first being the application of active learning for improving our case-based management. So in a real world system, there's some period of time that would elapse between maintenance decisions. It could be a couple hours or a couple of days even. So it's possible, since we do have access to a simulator, we could use that simulator to better learn how to make decisions during that downtime, rather than just gaining experience when we're making a real maintenance decision. We could also improve this by abstracting the state representation. So I mentioned that a a lot of states are very similar in terms of which action is optimal. And we do overcome that a little bit with our CBR procedure, but if we can abstract our state representation, that would allow us to search our state space more efficiently. So for example, maybe it's the case that the current elapsed processing time for each machine does not determine the optimal maintenance action. So we could remove that from our state representation altogether, which would decrease our overall state space and let us search that space more efficiently. Lastly, I think we would like to see the development of an industrial use case. Some of the experiments that I've showed here are largely simulation experiments, but certainly we would be interested in potentially applying this to a real world use case to see if we can improve upon maintenance decision making in a real system. So that is all that I have to share. I think with that, I would be happy to take any questions.
Thank you, Michael.